Hey everyone, and welcome. When we talk about AI hardware, all the headlines scream about speed and power. But behind the scenes, the real fight, it's not actually about making processors faster. It's a battle against a fundamental bottleneck in all of computing. It's a war against memory. Okay, let's just start with a number that is kind of hard to even wrap your head around. We are seeing chips with an absolutely staggering number of transistors. I mean, take the Cerebra's WSE3. It has 4 trillion of them. No, that's not a typo. 4 trillion. And all of that incredible power is being aimed at one single thing: running these massive AI models that are, basically changing our world. And the pace is just relentless. I mean, from AMD's MI100 just a few short years ago to NVIDIA's brand new Blackwell architecture, the industry is in a full-on arms race. So you'd think the whole competition is just about cramming more and more raw processing power onto a chip. But that is not the whole story. Not even close. And that brings us to the real fight, the one that keeps chip architects up at night. See, it's not just about making the processors faster. It's a battle against a fundamental law of physics in computing. I mean, it's a fair question, right? If we've got all this unbelievable computational horsepower, what's actually putting the brakes on everything? What's the holdup? Well, the antagonist of our story is this thing called the memory wall. It's this huge gap between how fast a processor can crunch numbers and how fast we can physically get the data to that processor. Think about it like this. You've got a world-class chef who can chop vegetables at lightning speed, but for every single ingredient, they have to walk down the street to a warehouse to get it. That's the problem. And this is really where you see the core conflict. On one side, you have pure compute. Modern chips can do trillions of operations, and each one is surprisingly cheap in terms of energy. But on the other side, you have data movement. Just moving the data from memory to the processor is slow, and every single one of those off-chip trips is wildly expensive when it comes to power. And NVIDIA's own guide kinda says it all. At the end of the day, it just doesn't matter how fast your processor is if it's constantly sitting around waiting for data. When that incredible processing power is just idle, waiting, all that potential is just gone, wasted. So how do they fight this memory wall? Well, chip designers have a secret weapon. It's this unsung hero that lives right next to the processor, and its whole job is to keep that hungry engine fed. Meet SRAM, that static RAM. Now, it's not the biggest pool of memory on the chip, not by a long shot, but it is by far the fastest. It's like the processor's personal high-speed workspace, a critical staging area that holds exactly the right data at exactly the right time, so you don't have to make those slow, expensive trips to the main memory. And if you want to see just how vital this stuff has become, just look at this floor plan of Google's TPUv4i chip. See that giant chunk labeled CMEM? That is all SRAM. It's eating up nearly a third of the entire chip. That's an enormous amount of precious silicon real estate dedicated just to this one thing: fast memory. But here's the crisis. As we shrink transistors down with every new generation, the logic, the part that does the math, it gets smaller way faster than the SRAM does. This creates a huge headache for designers. This super valuable high-speed memory is getting disproportionately big and expensive, and it's forcing them to make some really tough choices. And this challenge has basically forced the industry into a few different camps, right? Each one has its own philosophy, its own strategy for how to best use this incredibly valuable on-chip SRAM to try and win the war against that memory wall. First up, you've got the GPU approach. This is the philosophy championed by the big players like NVIDIA and AMD. Their main goal here is flexibility and just raw throughput for a whole bunch of different jobs. So their strategy is to build this huge, intelligent L2 cache using SRAM. Think of it like a big, shared reservoir of data. The hardware itself automatically tries to predict what data all the different little processing cores are going to need next, and it tries to keep them all busy without the programmer having to do anything. It's all about automated general-purpose performance. Okay, then you have Google's TPU, the Tensor Processing Unit, and they went a totally different way.
A TPU isn't trying to be a jack of all trades. It is a hyper-specialized accelerator that was built from the ground up just for AI.
So instead of that big automatic cache, TPUs use a massive software-controlled scratch pad called VMEM. There's no automatic guessing here. The compiler has to explicitly tell the chip, okay, move this data from the main memory into this super fast scratch pad right now before you need it. Yeah, it's more work for the software, but it gives the compiler total control to squeeze out every last drop of efficiency on those specific AI tasks.
And then, of course, there's a third way, the system on a chip, or SoC philosophy. And this is the one that, Apple has absolutely perfected in its M-series chips. Apple's whole strategy is about tight integration. With their unified memory architecture, everything, the CPU, the GPU, the AI accelerators, they all share one single central pool of memory. This completely gets rid of that slow, power-hungry process of copying data from one part of the system to another. And the result? A massive drop in latency and a huge boost in overall efficiency. So what you're seeing here really is that there's no one best answer. It's all about engineering trade-offs. You can see the contrast, right? The GPU approach is hardware-managed and automatic, all for flexibility. The TPU approach is software-controlled and manual, chasing specialized efficiency. And the SoC approach is system-managed and shared, aiming for low latency through integration. It's a really fascinating clash of priorities. So where does this all lead? Well, with SRAM scaling basically hitting a brick wall and chips getting as big as we can physically make them, the whole idea of a single, giant, all-powerful chip is being seriously challenged. This leads to the billion-dollar question for the next decade of computing, doesn't it? How do you keep making things faster when you can't just make the transistors smaller and the chips bigger anymore? And what we're starting to see is this really interesting shift towards something called disaggregation. Basically, instead of trying to build one giant chip, companies like AMD are connecting smaller, specialized chiplets together. And then you have even more radical ideas being explored, like in-memory computing, where the memory itself actually does the math, which almost completely eliminates data movement. The whole goal is to break that fixed link between compute and memory, and to create much more flexible and powerful systems. And so I'll leave you with this thought. The next great leap forward in AI, it might not come from a faster processor at all. Instead, it's almost certainly going to come from a smarter, more elegant way to conquer the tyranny of distance between our data and the chips that need it. The future of AI isn't a war for speed, it's a war for memory. Thanks for joining me.